deviatory component should be a function of what? It should be a function of the rate of deformation. So, if when you write the rate of deformation, let us just recall that the rate of deformation in general, in the most general form, this could be a gradient of velocity where I and j could be different indices. In a special case, I and j could be the same index. So, we have seen earlier, which is quite trivial, that you can write this as and this writing is nothing very special, it is just writing an identity, and the whole understanding is that this is like a tensor. You may write it in a matrix form also because you have two indices I and j, and basically you are decomposing it into a symmetric and a skew symmetric tensor. So, the first one is the symmetric one, next is the skew symmetric one. Physically this decomposition is very important, mathematically may be very trivial, but physical importance is that this is related to the deformation and this is related to the rotation. So, when you have a rotational sense, you do not directly associate that with deformation, because an element may have rotation without deformation, that is like a rigid body rotation, that is a special case. So, if you want to relate the deviatoric stress tensor component with something, what should be that something? I would say that the deformation which is appearing from here should be a natural, should be naturally related to the deviatoric stress tensor component, right. So, that is the first understanding. So, we have to first understand that what depends on what, because we are trying to develop something which is called as a constitutive relationship or constitutive behavior. What is a constitutive behavior? That is, if you have, think about say Hooke's law in linear elasticity. So, you say that stress is linearly proportional to strain within proportional limit of an elastic material. So, if you say that stress is linearly proportional to strain, that means you are somehow relating a cause with an effect, and that comes from the behavior of the material, because this you cannot generalize, it is specific to different materials, and that material constant will appear in form of a modulus of elasticity. So, modulus of elasticity is the gross response of the material against the applied loading condition. In say it is a tensile load and it starts getting elongated. Now, the manner in which it is going to get elongated depends on its modulus of elasticity, which comes from the inner characteristics of the material. So, it is a gross consequence of the material characteristics, and that is where it will be different for different materials. So, it comes from the constitution of the material, that is it is intrinsic to the behavior of the material, and that we call as a constitutive behavior. So, just like you have for solids constitutive behavior in that way, for fluids also you have constitutive behavior in that way, and that is how we have Newtonian fluids, non-Newtonian fluids, like that, because different fluids have different constitutive behaviors. So, we are interested to have a constitutive behavior or have a functional form of the constitutive behavior. So, the functional form in a very qualitative way should be, from our discussion, that tau ij deviatoric should be a function of the rate of deformation. That much we should appreciate qualitatively. Okay. Now, the question is, this function may be of whatever complex nature, and important thing is it will depend on what? It will depend on a deformation, rate of deformation, which is also a second order tensor. So, now we are interested to write a function where the dependent variable, so to say, is a second order tensor, this is a second order tensor, and the variable in which, or the function on which it is going to depend, that is the independent function, so to say, is also a second order tensor, and we are interested about the functional relationship between these two. This is not a very simple task. So, we will not look into the most general way of characterizing this, there is no very general way of characterizing this. So, we have to think about special cases, and the special cases are the cases when these are linearly related, which is like the Newton's law of viscosity. So, we will now consider a Newtonian fluid. So, if you have a Newtonian fluid, then this will be a linear function. That means the deviatoric stress tensor will be a linear function of the rate of deformation, just like Hooke's law for linearly elastic material, solid material. So, the question is now how we are going to write it. We have to keep in mind that we are now interested to write a transformation that maps a second order tensor onto a second order tensor. Earlier we wrote a transformation which maps a vector onto a vector. If you recall the Cauchy's theorem, the traction vector was mapped in terms of the direction normals or direction cosines of the area which was chosen to evaluate the stress tensor, the traction vector components, and that mapping was successful through a second order tensor which is the stress tensor. So, the second order tensor was such that it mapped a vector onto a vector, that much of mathematical understanding we had. Now, we are in a situation where we have to map a second order tensor onto a second order tensor. So, there should be some intermediate transformation, and that transformation is a fourth order tensor. So, a fourth order tensor is something which maps a second order tensor onto another second order tensor. So, this linear function is written in this form: tau ij is equal to a fourth order tensor, say C I j k l and a second order tensor. So, what is EKL? EKL is like okay. So, this is EKL. So, E is like the rate of deformation, just this form, just I and j are replaced by k and l. So, this is like Eij, whatever is written here, okay. Just a symbolic way, so that we do not have to write the big thing again and again, that is just a symbolic way of writing it. Now, you look into this. So, what are the repeating indices here? So, you can specify, you can fix up I and j whatever you want, but you cannot fix up k and l whatever you want, because it is summed up over that, because these are repeated indices. So, you have basically summation over k and summation over l, each running from 1 to 3, but the more important thing is that so k and l could be from 1 to 3, I and j also could be from 1 to 3, those are free, but you could have I equal to 1, 2 or 3 or j equal to 1, 2 or 3. So, how many combinations with C I j k l are possible? In the most general case, 3 into 3 into 3 into 3, 3 to the power 4. So, you could have 81 components of C I j k l, and that is the most general constitutive behavior for a Newtonian fluid. That means, if it has no other special effect, then you would require 81 independent constants to specify its constitutive behavior. That is not again a very simple thing. So, of course, we are not going into that what would be the picture if we had 81 constants. We will see that those will be reduced to again fewer number of constants even in a more general case, because we know tau ij equal to tau ji. So, from that symmetry we can at least reduce a few in number. So, we will not go through that route, but we will at least keep in mind that mathematically speaking, if you do not use the symmetry of tau ij, you have 81. If you use the symmetry of tau ij, 36. So, you will I will leave it on you as an exercise to show that if you use tau ij equal to tau ji, the 81 constants may be reduced to 36 constants. But the thing is, that is also not something which is very tractable. Think about a problem where you are a practical problem where you require 36 material constant properties to describe a flow. I mean, in a very general situation that might be the case, but that is not a very common case in engineering or even in science, it is not a very common case. So, we will do in this course or we will address in this course something which is perhaps the simplest of all these cases, but the most commonly encountered one, that is we will consider the very special case of a homogeneous and isotropic fluid. So, the special case that we consider is homogeneous and isotropic fluid. Homogeneous fluid and isotropic fluid. So, till now what assumptions we have made? We have made assumptions, first of all stationary reference frame, that is with which we started our equation, then a Newtonian fluid, special case homogeneous and isotropic Newtonian fluid. Okay. So, now the question is that when you have a homogeneous and isotropic fluid, what is the special characteristic that you have? So, what should be the dictating factor for a homogeneous and isotropic? So, what is homogeneity? So, homogeneity means it is same at all points in the flow field, that any property is same or position independent at all. So, this is related to position independence. So, the constitutive behavior does not vary from one point to another point, and isotropy means direction independence. What is the hallmark of that? Say if you have coordinate directions, say x and x1 and y1, and if you measure or if you try to assess a constitutive behavior on the basis of that. Now, if you have a transformed coordinate system still orthogonal, but let us say x prime and y prime with a rotation, this does not disturb the constitutive behavior, although the orientations of the axis that you have considered for describing the behavior, those have changed, but in terms of that new axis the constitutive behavior still remains the same, the description still remains the same, that is called as an isotropy. So, we are going to think about a homogeneous and isotropic fluid. So, if you have a homogeneous fluid, the thing that we will immediately conclude is that Cij should be independent of position. Otherwise, if Cij is a function of position, it loses its homogeneity. What would be the consequence of isotropy? That is something which we need to look into more details mathematically. So, for isotropy, to say that you want to form something like you have the fourth order tensorCijkl, how could you convert this into a scalar? Because see, let us say our objective is to convert or transform this one into an isotropic scalar. Okay. Let us say there could be many ways of doing it. Let us say what you are given are vectors. So, using vector, how can you convert this into a scalar? Forget about isotropy. How can you use vectors to convert it to a scalar? Let us say you have, how many vectors would you require? First you say, this is just from common index notation understanding, you can say 4, because if somehow you can sum it up over these indices, then it will have no free indices, and that then it will become a scalar. So, if you have say 4 vectors a, b, c and d, you know vector is characterized by one index. So, this say it has ai, just for its index notation, say this is bj, this is ck, this is dl. Just mathematically, now if you have say this ai, bj, ck, dl, then and if you write it in this way, that means there is an invisible summation over I, j, k, l. So, at the end whatever comes out does not have any index and it is a scalar, right. So, you can employ 4 vectors, 4 independent vectors to convert a fourth order tensor to a scalar, that we can understand. But we are interested for a special type of scalar which is an isotropic scalar. Now let us see that what can lead to isotropy if you are dealing with 4 vectors. So how can you say, just look into this example. Here we had 2 vectors. When we talked about this rotation, actually we talked about a vector, say maybe one vector oriented along x, another vector oriented along y, and this vector combination was rotated, and after rotating this vector combination, the property or the constitutive behavior whatever is described through the new orientation, that is same as whatever is the description through the old orientation. That is the implication of isotropy. So what is the meaning? The meaning is very interesting. If you do not change the angle between the 2 vectors, then it does not change. So when you, what is rotation? Rotation is something which preserves the angle between whatever vectors were there. So as if you are rotating these vectors like a rigid body, keeping the angle between the vectors same. So if you have vectors a, b, c and d, and if you somehow preserve the angle between these two taken in pairs, say a with b and c with d, maybe a with c and b with d, and a with d and b with c, these are the possible pairings. So with these possible pairings, if somehow you keep the angle between these as unaltered, then no matter whatever is their orientation in space, so long as the relative angle does not get disturbed, it should give back the same behavior. That is the meaning of isotropy. So if you have vectors a, b, c and d, so what kind of combinations you can have taking all those 4? You can have a dot b and that corresponding combination is c dot d, then you could have a dot c, b dot d and a dot d, b dot c. Why dot? Because dot directly gives the angle between 2 vectors. We were talking about the angle between 2 vectors. So if we consider the dot product, that returns sort of angle between the vectors. So if that is preserved, then isotropy is preserved. So why such a combination? Because you see that this will give rise to a scalar. So if you take these in pairs, these are individually scalars. So the combinations, all combinations of these ones will form a general isotropic scalar involving the 4 vectors a, b, c and d. So this we can write, so let us form that scalar. Let us say that scalar is equal to a dot b, c dot d, some multiplier of that, say alpha, because the scalar multiplier does not change its any characteristic. So alpha is just an arbitrary scalar multiplier, plus beta into a dot c, b dot d, and let us say plus gamma a dot d, b dot c. Okay. So we have just made a linear combination of these 3. Our objective is to ensure that we get an isotropic scalar. So now what we will do, we will write it in terms of the index notations. So if you write it in terms of the index notations, how we are going to write it? So we are going to write it in this way. This is the first term that we are writing. Just look into the corresponding term. See, a dot b may be written as ai bi, because it is what, a1 b1 plus a2 b2 plus a3 b3, that is the dot product. You take the corresponding components and multiply with each other, sum it up, that is how you get the dot product of 2 vectors, right. So there is an invisible summation like this, and here also it is like this. keep in mind I and k are just dummy indices. So, in place of I you could write j, in place of this you could write whatever. Okay. Similarly, let us write the other terms plus okay. Now you see that we wanted to get it as an isotropic scalar. What is that special isotropic scalar that we are looking for? We are looking forCijkl into Ai Bj Ck dl, right. That was the form that we are looking for. Here in the form you do not have the indices A, B, C and D as different. So, if somehow we can convert these indices of A, B, C and D as entirely different, like one I, another J, K and L, then we would be able to compare this form with this form that we have for our constitutive relationship. So, our next objective will be to convert these forms like AI, BI, CK, DK to a form like AI, BJ, CK, DL, that form. So, how do we do that? Let us say you want to convert BI to BJ, that is our objective, say because you have AI, next you want BJ. So, you want to convert BI to BJ. So, there is something very useful in terms of index notation which is called as Kronecker delta. So, this is given by, this is just a notation. So, this is defined in this way, delta ij such that this is 1 if I is not equal to j, if I is equal to j, and 0 if I is not equal to j. Okay. So, this is just a notation, that means if you have only I equal to j, this is 1, otherwise 0. Now, let us see. Let us say we want to write Bi delta ij. What is this? See, you have to keep in mind that when j is equal to I, so rather you may also think it as j equal to I or I equal to j, whatever, like when they are equal. So, think about that only when you have I equal to j, then only this is 1. So, there is only one case when this is equal to 1, and that is when this I is j, right. So, this becomes Bj, because only when I equal to j, then these two indices are equal, that is 1, otherwise it is 0. So, you can see that this is a very simple and elegant way of switching the indices from I to j, j to I, like that you can play with this. So, what we will do, we will use that switching index here. So, this Bi we will write Bj into delta ij. We will keep Ck because that is what we want. We want to convert dk to dl. So, what we will do? We will have dl into what? Delta kl, right. Similarly, let us look into the second term ai, let us say we keep ai, bj is there, we want to change ci to ck. So, what will be the transformation? Ck into delta ik. Okay. It is transformation from I to k, that is why delta ik. Then we want to change dj to dl. So, dl into delta jl. Similarly, the third term you have AI, you have Bj, then you want Ck, so Cj will become Ck delta Jk and dl into delta IL, right. So, if you write in this way, see what is our desperate act. The desperate act is we want to write the right hand side just in a form AI Bj Ck dl, okay. So, in this using this simple notation we are able to write it in this way. So, let us write that then. So, what at the end we can write? We can write that you have now the right hand side which we want to express as, say, the left hand side asCijkl into AI Bj Ck dl, we want to make it an isotropic tensor, and the right hand side we have expressed in terms of an isotropic tensor with, again you have AI Bj Ck dl, that is like they are common for all terms, then you have alpha delta Ij delta Kl plus beta delta Jk delta delta Ik delta Jl and from the third term gamma delta IL delta Jk, right. So, from here it follows that you should haveCijkl is equal to alpha into delta Ij delta Kl plus beta delta Ik delta Jl plus gamma delta IL delta Jk, where delta Ij is defined as above. See, with this simple exercise we have come up with a very interesting and advantageous conclusion. What is that? We started with 81 independent constants in general to describe the material property. The material property is given by theCijkl. Now, how many constants you have? 3 independent constants, alpha, beta and gamma, because delta Ij, like these are like, you know, that is either 1 or 0, okay. So, we can see that, and these are position independent. So, these are really constants. If these were position dependent, these could be also functions of position. So, we can say that for a homogeneous isotropic fluid we are now able to come up with 3 independent constants. We may reduce it even to less because we have not yet exploited the symmetry of tau ij, that we have never used. We must have tau ij equal to tau ji, that we have seen from angular momentum conservation. So, the next step is we use the symmetry, that is you have tau ij equal to tau ji. So, tau ij is what? Tau ij isCijkl Ekl, that must be equal to Cjikl Ekl, right. So, what it follows is that you must haveCijkl equal to Cjikl. So, this must be also equal to Cjikl. So, how do you write Cjikl? Just switch I and j here. So, that will be equal to alpha delta ji delta kl plus beta delta jk delta il plus gamma delta jl delta ik. We have just switched I and j. Okay. Now, you see First of all, what is the relationship between delta ij and delta ji? They are the same. Delta is just a symmetric tensor. That means when you equate these two get nullified, cancelled, they are the same. For the remaining ones, you see delta ik delta jl is this term, one is coming with a coefficient beta in the left hand side, in the right hand side that is coming with a coefficient gamma, that is the only change. And for the other term here, this term is same as, like the coefficient of gamma here is same as the coefficient of beta here. So you can just combine that in a simple factorization and write that beta minus gamma into delta ik delta jl minus delta jk delta il, that is equal to 0. Okay. Whatever is there inside the bracket, in general this is not 0. Special cases are there, but there are general, I mean there are certain terms which will not be 0 when the indices are equal. So this in general for all cases, since this is not equal to 0, for all cases if you want to make it satisfied, only thing you must have beta equal to gamma. Okay. Because what we understand is that the second term in the bracket, in some cases it is 0, it is true, but in all cases it is not 0, but we must have a constitutive behavior that should be true for all cases. So now you see, now we can writeCijkl is equal to alpha into delta ij delta kl plus beta into delta ik delta jl plus beta into delta il delta jk. So how many independent material constants we have? 2. Keep in mind that there is a exact analogy with mechanics of solids. If you have a solid material, it is a elastic material, then how many independent material constants you require to specify its behavior? 2 independent constants, modulus of elasticity and Poisson's ratio. You can express the rigidity modulus in terms of any of these 2. So you require only 2 independent material constants. Here also it is totally analogous. So you are requiring 2 independent material constants to specify its behavior. What are those material constants? That will come from the physical understanding of these terms. So when we want a physical understanding of these terms, we will now write the expression for tau ij, that will give a physical understanding of the term. So tau ij is Cijkl into ekl. So we will multiply this with ekl. So when you multiply this with ekl, so you have alpha delta ij, let us just write it in a expanded form, delta kl ekl plus beta delta ik delta jl into ekl plus beta delta il delta jk into ekl. Okay. Let us now simplify these terms. This simplification is easy, it is quite simple. If you consider, let us say this term delta kl ekl, you tell what should be the corresponding simplification. Let us erase this part and we will write the simplifications here. So delta kl ekl, say we want to write it. How do you write it? You have to keep in mind that this delta is 1 only when L equal to k. So this you can write as ekk or ell, right, because in all other cases it is 0. What is this actually? This is again not one term, it is E11 plus E22 plus E33, because it is a repeated index. So you have a summation basically. So what is E11 plus E22 plus E33? Let us just write it. E11 is this is just by using definition of Eij, then E22 and E33 okay. What is this? This is the divergence of the velocity vector. So, we can clearly understand that this has something to do with the compressibility of the fluid, volumetric rate of volumetric strain of the fluid. So, the first term we can understand that it should be related to the rate of volumetric strain of the fluid. So, tau ij's first term we have come up with. So, tau ij is equal to alpha into delta ij into ekk. Then next terms, let us write the next terms. Next terms you see that what are the indices that you play with here. So, what are the repeated things? You have k as repeated and L as repeated. Okay. So, there are special cases of k and L when this term is non-zero. What is that? When k is equal to I and L equal to j, right, because then only these deltas are non-zero. So, the next term will be beta into Eij, right, because this I and j should be something for which delta Ik and delta jl are non-zero, and that is there when I equal to I becomes k, or rather k becomes I and L becomes j, because you are writing a summation over k and L. You are trying to find out those values of k and L for which this term is not 0, and that is only k equal to I and L equal to j. The next term, so you have here again you see what are the repeated things, you have k and you have L. So, again when L equal to I and k equal to j, so plus beta Eji, and the rate of deformation is a symmetric tensor, we have already seen. So, Eji is equal to Eij, right. That means we are able to write tau ij in a form alpha into delta ij into ekk plus 2 beta Eij. Okay. Now, the question is how physically we may relate these coefficients alpha and beta. To do that, we should understand one very important thing, that where from the effects of these come. First you have, let us say you have beta. So, where from the effect of beta is coming? Let us write what is 2 Eij. So, what is 2 Eij? You have 2 into Eij is half of this one. Okay. So, this is considered as very special case of a one dimensional flow, which we did at the very beginning when we are discussing about viscosity, that you have only one component of flow, say u component of velocity, other component was not there. We wrote something very loosely from physical understanding that tau equal to mu du dy, right. So, when you have say one component only u, other component say u1 only you have, and say you are thinking about the gradient along y, so j equal to 2, and other term is not there because only one component of velocity is there, say you can write this as du1 dx2, that is like du dy. So, you are relating that with some tau. Remember this tau is not the total but tau deviatoric, which is related to the deformation. So, that is related to this through a coefficient, and that we have already seen. Therefore, in the general notation this beta must be the viscosity of the fluid mu, right. So, see, from mathematics we are converging to the physical understanding, and this is very very important. Continuum mechanics is a beautiful subject, it can make you agglomerate physics and mathematics very nicely. So, this is mu. This constant is not so well known to us till now, whatever we have discussed, but it is given a general notation of lambda. This is called as second coefficient of viscosity. We will see later on that what is the significance of this, physical significance, we will see in details, but just a name, second coefficient of viscosity. Why? Because already you have a viscosity like mu which already is there. So, if you want to have a different coefficient, but we have to keep in mind that this is related to sort of angular deformation of the fluid and this is related to volumetric deformation of the fluid. At least qualitatively we can understand the significance of these two terms. One term is related to the angular deformation, one term is related to the volumetric deformation. Angular deformation means shear type of deformation. Now, this is the deviatoric stress tensor only, but what about the hydrostatic one? So, tau ij, there is one tau ij hydrostatic, because the total tau ij is tau ij hydrostatic plus tau ij deviatoric. So, what is tau ij hydrostatic? That is, consider a case when the fluid is in static equilibrium and then even there is a stressing condition because of the pressure distribution. So, how do we write it in terms of this tau ij? See, you have to keep in mind that it is a pressure effect is like a normal force effect. So, it is there only when I equal to j, because I equal to j gives the normal components. So, it should be something which is 0 if I is not equal to j and which should be 1 if I equal to j multiplied with the magnitude of that. So, it should be something multiplied with delta ij, that is clear, because it should not be non-zero if I is not equal to j. What should be the multiplier? That is the corresponding scalar of it. So, what is that? That is because of pressure, but you have to keep in mind that pressure by default is compressive in nature, whereas our positive sign convention for normal stress is tensile. So, it should be minus p. Okay. So, you come up with the final form where what is the tau ij total, that is tau ij hydrostatic plus tau ij deviatoric. So, this is tau ij hydrostatic plus tau ij deviatoric. So, what is that? So, you have lambda. So, first let us write the hydrostatic minus p delta ij plus lambda into ekk into delta ij plus 2 mu eij, that is the tau ij. So, we have come up with an expression for constitutive behavior. It has what unknowns? What are the unknowns here? See, eij has unknowns as velocities, because it is written in terms of gradients of velocities. So, you have velocities and you have pressure. So, in the equation of equilibrium, see what is our objective at the end? To solve for the unknowns. So, where we have landed up? We have landed up with an expression for this tau ij which is expressed in terms of unknowns as velocities which are already there plus a new unknown has appeared which is pressure. So, in the next class we will see that first of all what are the physical significances of different terms, what is the physical significance of lambda, how it is related to mu, and then how we can come up with an equation in the final simplified form where we substitute this constitutive behavior of tau ij in this expression. That we will take up in the next class. Thank you.